we've been talking a little bit about how to run. You have multiple processes running concurrently. How to communicate between them, things like that. We've talked about how the operating system organizes the resources of the system to be able to provide each of many processes. It's the impression of it having its own data to run on, and so and that all works very well. And now the question is: suppose we want to do better than that. Suppose we want to actually go back to thinking a little bit about making our programs run faster and faster and faster. And that's a conversation that we started when we started thinking about pipelining. So today we're going to do a sort of a look through the system. We're going to spend a little bit of time, the last half of the lecture will be more about what happens if we try to put multiple betas together into a multi-core beta system. And there's some interesting problems we have to solve. And in some ways they're analogous to some of the problems we had to solve when we pipelined the system, where we start getting unexpected interactions that we have to say, okay, can we solve that one in hardware? So, just a reminder that the performance of your program, the time it takes to run your program, is actually made up of several factors, and we've been working on architectural solutions to each of these factors, right? So the number of instructions in your program, if you have a good optimizing compiler, if you have an instruction set that is easy to compile into and perhaps produces more optimal code, that's all good. The throughput of the system in terms of cycles per instruction, and we worked hard when we did our pipeline system, for both our regular beta unpipelined and also the pipeline beta, to basically try to execute one instruction per cycle. So one question is, can we do better than that? And then finally, we're always interested in whether it's a uniprocessor, one-stage system, or whether it's a multi-stage pipeline, what can we do to make the clock run faster? Okay, so pipelining we introduced to simply take a big clock cycle that had time to do everything that was needed for a complete instruction and divide it up into sections so that we could then overlap the execution of the instruction. We could have 5 instructions all operating in different different parts of their different stages of their processing, but we could have them all operating in parallel, and our T-clock got reduced by, well, maybe not 5, but maybe a factor of 4 or 3 or something like that. Anyway, it was an improvement. The cycles per instruction is a little bit more challenging. We have the sort of ideal, what we can get if everything is running smoothly and there's no hazards that we have to take care of. So that's sort of the CPI ideal. And for our design, we've set that currently to be 1, and we'll look into some strategies for making it less than 1 today. There are some other factors that contribute, the so-called CPI stall, which is sort of a generic name that we use to represent all the additional cycles that are needed, or on the average it's fractions of additional cycles that are needed, to deal with the various sorts of hazards, data hazards, control hazards, memory latencies, and cache misses and things like that. And typically, as we try to build very high performance systems, we can look at this architecture and say, okay, we've got a great CPI ideal, but then it's all the dependencies that cause us to start getting into trouble, and basically our performance degrades. And as we'll see today, there's a bit of a diminishing returns that we get, and CPI stall becomes more and more, looms larger and larger as the thing that gets in our way of getting our programs to run faster and faster. So we have a 5-stage pipeline. This should look familiar to you. Basically, the instruction spends 1 clock cycle in each stage, unless of course it's stalled, unless of course it's stalled in a stage, in which case it may spend multiple clock cycles. So that's the thing that might reduce the effective CPI. But the best we can do is one clock cycle for each pipe stage. So the throughput of the system is 1 instruction every clock cycle. If we think about what happens in the write-back stage, every clock cycle, in theory, we're finishing a new instruction. Instructions with latency issues, particularly if we have large caches or memories whose latency, whose access time is longer than our desired clock rate, every time we then do a load or a store or an instruction fetch, these are all things that will degrade performance. And the other thing about the pipeline is pretty inflexible. Once, for instance, a particular instruction gets stuck in the RF stage, waiting, for example, for a load to reach the write-back stage so you can do the bypass, the load-to-use data hazard that we had to solve. What happens is that everybody else is, we're introducing no ops. Everybody behind the instruction in the RF stage is just has to stand in line and wait because there's a slow poke in front of them. And so those are sort of like, well, are we stuck with that? So that's part of the questions we're going to ask today. So what can we do to fix up our 5-stage pipeline performance? Well, we can look for deeper pipelines, go to a 10-stage pipeline or a 20-stage pipeline in the hopes of taking our current clock cycle and dividing it by half again. The trouble, of course, with deeper pipelines is we have more instructions executing in parallel. I mean, in some way that's good, unless they interact. And you can imagine, so if there's a branch every 6 instructions or so, having a 20-some-odd stage pipeline seems like a great idea, except that what happens is that the branch is forever causing the pipeline to be flushed because it has to throw away the things in the IF stage or however many pipeline stages the IF stage turned into. And so what happens is CPI stall starts to grow. So deeper pipelines are good for T-clock, but they tend to make it much harder. CPI stall tends to start to get larger. We could think about issuing more than one instruction at once. Is it possible for us to do 2 instructions at a time or 3 instructions at a time? So we'll look at that. The Holy Grail, and in fact, the notion of a wider pipeline, superscalar, so-called pipeline, is something that you own. You also own a pipeline that performs out-of-order execution. So another solution to our, oh my goodness, I have to wait for that stupid load to get to the write-back stage, sort of holding up all the processing, is if we can identify instructions that can be executed, we can get started on them. So just because you've written your program in a certain order doesn't mean that the hardware might not be able to figure out how to rearrange the instructions in order to get better execution. We'll discover in order to make all this work, we're going to need the notion of branch prediction. Branches, happens frequently enough that we simply can't throw up our hands and really restart the pipeline every time we hit a branch. So now we're building hardware to guess which way the branches go. And if we guess correctly, we don't basically have any penalty for the branch. And more than that, suppose we actually can do speculative execution and we can actually execute instructions from both ways of the branch. And once we finally figure out what the branch is going to do in some later pipeline stage, we can throw away the instructions that we started to execute that we no longer wish the result from. So speculative execution. So all of this is baked into the Intel CPU that you have. Intel is trying very, very, very hard to run as many instructions in parallel and hope to do it in the most effective fashion. Okay, and it all works because we're able to find instructions that can run in parallel. So look at here's just a standard piece of sequential code that I wrote. I've rewritten it here, and so instructions on the same line can actually execute together because they don't have any dependencies. The red arrows show dependencies, and what do I mean by a dependency? That a result produced by, in this case, by the load instruction provides a source operand for in this case, the compare less than instruction, right? And so we obviously have to wait until the load computes its answer before the compare instruction can run. On the other hand, if we look here, we can see that these 3 loads can really all run in parallel. They don't conflict with each other. So the question is, how much instruction level parallelism is there? How much ILP can we find? And then what sort of hardware do we need to build to actually do it? And the answer is, we can do pretty well up to a point. So, maybe we can get a factor of 2 out of this if we're lucky. On the average, the number is somewhere around 2. We obviously have some bingo situations where we can do 3 or 4 instructions, but those are traded off against the times when we, unfortunately, can't, if we're going to do in-order execution, we can't get ahead. One of the things that a lot of compiler writers have noticed is that, in fact, even though there tends to be a lot of dependencies within an iteration of a loop, if you think about one iteration loop to the next, often those are largely independent. Right? In other words, you could do, the 10th iteration of the loop and the 11th iteration of the loop are probably accessing different pieces of data, doing some local computation, whatever they're doing. But the idea is that often, iteration to iteration, there's an opportunity for a lot of parallelism. And so that gives us some insight into how we might structure our code. We might do a little bit of loop unrolling and carefully write our instructions for 2 iterations of the loop so they interleave, so that we have a lot of now legitimate ILP, instruction level parallelism. So how deep can we make a pipeline? The pipelines that you have, I think, are mostly if you have Nehalem processors. So you have most of us now have Core, the so-called Core, Intel Core processors. So those have a 16-stage pipeline in them. Okay, but why stop there? Why not have a 20-stage pipeline? In fact, the Pentium processors, I think, had a 22-stage pipeline. Or maybe it was 24, but it was higher. But why not a 57-stage pipeline? And the answer is that we have to be, we can't just arbitrarily take every, a piece, extraction of the execution of an instruction and break it in arbitrary places. There's certain operations that are, if we're doing addition, we can sort of split the addition in the middle and do the low half and then save the carries and do the high half. So there are some opportunities for splitting operations. Other operations like multiply, it's a little harder to figure out how you do the low half and the high half in parallel or something like that. So if we imagine that we're breaking our big task of time t into many smaller tasks in an n-stage pipeline, and there's a little bit of overhead, the pipeline registers between each pipe stage. So where does that overhead come from? Well, it's the propagation delay of the register, coming out of the register, there's a little delay, and then there's a setup time into the downstream register. Those represent fixed costs, in other words, and as you sort of fool around with a little arithmetic, right, you can say, well, if I have to accumulate, in each pipeline stage a certain amount of overhead, and then the speed up is this new improved speed, divided into the total, the time of the total task, and we were hoping for a fairly good amount of speed up. What we discover, though, is as n approaches infinity, as we get more and more and more pipeline stages, we sort of say, oh my God, the overhead turns out to be the dominant factor. It's going to limit our performance. And you can read papers that, maybe that number is 57. You can't get any more than 57 pipeline stages. After that, your performance never increases no matter how much more you divide it up. Okay, so often it's the case with most of our mechanisms that the overhead accumulates, right? And that prevents us from going any farther, because now we've sped up things as much as we can, and the overhead starts becoming the dominant factor. Okay, so multiple instructions at once. What can we do? Can we do, suppose you have integer and floating point arithmetic? Well, it's pretty obvious that those are separate pieces of hardware anyway. So maybe if I have an integer instruction followed by a floating point instruction, both of those could run at once. And that was the simplest form of ILP that used to exist, many decades ago. And then, and processors got more and more sophisticated and provided enough enough ALUs and branch offset adders and things like that, so they could basically execute 2 instructions at once or 4 instructions at once. For a while, there was a lot of hope that that number could keep going up. As a practical matter, it seems to peak out somewhere, maybe a little under 2 or a little over 2, but certainly is not 4. Even though the hardware is there to catch little bingos, on the average, we're not able to get n super large. Here's a picture of what your modern processor looks like, right? And you can see that it's roughly, you can sort of see there's fetch, there's, decode and read the registers, there's the functional units, there's something here called the reorder buffer, and then we rewrite things, back into the register file. So this is, the flow top to bottom is not like, okay, I've never seen this before, but there's a lot of interesting little pieces in here. So there's a whole, in fact, a fairly, when I'll show you the picture in a moment, branch prediction takes up a lot of hardware these days. Okay, a lot of hardware. And the whole idea there is that it's keeping track of the history of your program and what it's done on previous iterations of the loop. Last time I went to this branch, what happened? It's basically trying to do a very sophisticated statistical analysis to figure out if it can guess which way the branch is going, then the instructions that it fetches are going to be executed. If it mispredicts, then all those instruction fetches that it's been doing may in fact be wrong. Now, the fetches that sort of happen while the earlier instructions are busy executing. So if the branch decision happens down here somewhere, it can be the case that there's many other instructions in flight. We want to make sure those instructions are good. And so we try to build branch predictors that have very high accuracy in the upper 90%. And there are people successful these days, although it takes a lot of hardware. Once we have instructions that we really are ready to execute, we sort of line them all up in front of the like queues in the bank in front of the different operational units. And what the reservation station is doing is it's waiting until the operands for the particular instruction are available. So the idea here is that we're waiting for, if there's some dependency, what we're doing is we're waiting here before we start execution until we actually have those register values. Other instructions can sneak in front of us. If their operands are ready to go, they can get, they can sort of sneak in line here and get executed. Right? So this notion that we actually have lots of things we could be executing is when their operations are available, we actually say, okay, then we shove them into the functional units. Meanwhile, instructions that were logically behind us may cut in front if their operands are available sooner. And then at the end, there's this fairly complicated piece of logic called the reorder buffer, whose job it is to take all the results computed, higgledy-piggledy in some sort of order, and basically keep track of them, and then make sure it writes the results into the register file in sequential order. In other words, if I have I have an instruction that writes into R3, and then 5 instructions later, I have another instruction that writes into R3. At the end of the day, the value that needs to be in R3 after everybody is executed has to be the result of the second instruction, even if they got executed in some different order. So we're allowed to reorder the execution of instructions, assuming that we're ready to put at least the side effects, the writing the value back in the register file, we're ready to put that back in order again. So there's a lot of hardware that goes into that. Here's an interesting picture. This is actually a picture of a Core i7, a Nehalem thing. There's actually 4 cores here with a huge L3 cache. So you have a 4-core processor. This is an actual a picture of one of those cores. Here's sort of all the different pieces. You can see that the execution units, which is sort of where all the work is going on, is actually just a small piece of the rest of this logic, which is involved in branch prediction and instruction decode and out of order. This is the reorder buffer, and so this is all pretty. The amount of transistors that go to work as opposed to going to an enormous amount of effort to look for things we can do in parallel, parallelism is really costing us. And to give you a sense, not to scale, the beta is actually much smaller, okay, is that our very simple little beta is really just a small fraction of the logic that you see for one of these cores, right? So, not to make us all feel like pygmies, but the thing that we carefully designed and we're justifiably proud of designing really fits in some little tiny dot in the corner of a Core i7 Nehalem die, right? So there, you can say, what do they do with billions of transistors? Well, that you can, I've tried to give you a little hint of where all those transistors are going, big caches and things like that. So there are huge overheads associated with high performance execution. So we'll ask the question in a moment, could we get away with maybe lots of little guys instead of one big guy? So the power and complexity grow superlinearly. In other words, if you double the number of out of order execution things you're ready to do, you will pay more than double the power, more than double the complexity. It gets out of hand very quickly. extreme design complexity. It takes a lot of work to figure out whether a new generation processor actually will execute all x86 programs correctly. And in fact, you know, in the modern world of designing integrated circuits, you think, I'm going to go off and design one. You say, great, but remember, for every week of design, you're going to have a month of testing, right? And so, you know, making sure that it all actually works is actually much more complicated than designing it to begin with. And you very quickly learn that designing it so it is correct is much better than, like most of us do design or write programs, where what do? You hit compile and rerun it, and if it doesn't work, somebody will tell us, right? Well, you know, for big errors, that's easy. For little subtle errors, you know, you just have to hope that somebody wrote a test that figured out that adds that occur exactly 4 instructions after a subtract on Tuesdays don't work, right? I mean, that's the sort of, you know, bugs that are you know, what give Intel engineers nightmares. Okay, so the bottom line is that we've sort of gotten to the end of the road of figuring out how to execute many instructions in parallel. We're you know, there's incremental little improvements, but we're not going to do much better than we're doing now. So we have to exploit 2 other types of parallelism. Okay, so LP stands for level parallelism. So we have ILP for instruction level parallelism. DLP is data level parallelism. And as soon as I show it to you, you go, oh, well, that makes sense. Okay, and then the final thing is thread level parallelism, so having multiple processes running, and we've already talked a little bit about that, but that's where the multi-core stuff comes in. So we're going to talk about a little bit about those. Okay, so we have multi-core processors, and what we're seeing is that we reach this sort of, get past the knee in the performance curve, and you know, we have a Core i7 here. Well, to get, you know, to make a dramatic increase in performance, the complexity and the cost is going to skyrocket. And in fact, it's not even clear if we get to this performance level. There may be some sort of asymptote that we're running against. Okay, so on the other hand, if we look how this compares to, say, a modest performance core, you can see that we can get, you know, half the performance, okay, for dramatically less cost, for much less than half the cost. And that suggests that if I, you know, use 2 cores or 4 cores, I'm able to get much higher performance at dramatically lower cost. Right? And so that's really why everybody is focusing on delivering more and more cores. And you know, that goes back to that old thing I said many lectures ago about SMOP. Anybody remember what SMOP was? S-M-O-P? SMOP. A small matter of programming. Right? In other words, the hardware guys are saying, oh, wow, look at this, 12 cores in one Xenon package. You know, that'll be $2,000, please. And you go, that's great. Now I just have to think about how to use 12 cores to make what I want to do go faster. And they say, well, good luck with that. That's a programming problem, not a hardware problem. So the idea is that multiple cores are the direction we're heading in for sure. The hard part is figuring out how to use them, and in some ways, that's one of the big challenges in the for the current and next generations of computer scientists. Okay. Now, before we fall in love with multiple cores, let's do a little bit of analysis. So, Gene Amdahl, who actually died earlier this year, he was in the news. He was actually a fairly famous computer scientist at IBM. And then later on he had his own company called, surprisingly enough, Amdahl Computers. Anyway, Gene Amdahl has this, did this very simple analysis, but what is actually pretty illuminating, right? So, what we're going to do is we're going to try to measure the speed up that's possible. And what we're going to take some fraction f of what we're doing. It would be great if it was all of it, but typically we're able to speed up something. You say, Chris, I have a new idea, multiplies are now twice as fast. Okay, and that seems on the surface of it, okay, well, it's worthwhile, twice as fast is good. But the real question you should ask yourself is, wait a minute, how many multiplies are there? What fraction of my program is multiplies, and if those are twice as fast, what sort of speed up should I expect? So the sort of calculation is pretty easy, right? What we're going to do is that the fraction of that wasn't sped up, okay, so that's 1 minus f, takes the same time as it always did, okay, and then I have the fraction that was sped up, okay, is now taking, a much shorter amount of time. Right? So we can sort of get this overall speed up here, from this formula. And so the idea is what we've done is taken some big computation, we've taken some fraction of it and sped it up, so the overall time has gotten faster. Okay, there's nothing very mysterious about this. This is just sort of being slightly careful about making sure that you are accounting for the things that you're speeding up correctly. But the thing that's illuminating about this, there's so many conversations about making things faster that forget that. Somebody runs in and they told you that they sped up this part of the program dramatically, okay, and then you go back and you say, but the program is still taking 2/3 of a day to run, and you say, yeah, but it used to take 2/3 in 5 seconds, and that 5 seconds went down to nothing. And you say, well, that's good. So you have to, this is always a good analysis to make. Alrighty, so suppose I have a multi-core system, and I'm offering to speed up things, okay. So here's the overall speed up. Suppose I actually have, I take 90% of everything I'm doing and I'm able to speed it up almost infinitely. I can make it almost free to do. The overall, the vast majority of everything I'm doing is now much faster, but the overall speed up is limited to 10 because there's still that 10% that wasn't sped up and it is as slow as it ever is. Okay, so the overall speed up sort of goes like that as the amount of speed up you can get on the fraction you're speeding up gets faster and faster. So it's limited by the amount. And now the question you should ask yourself, if I have a 1,000-core machine, what does F have to be? So to use a 1,000-core machine well, suppose we wanted a factor of 1,000 speed up. You might say, look, you guys, you tell me you're hot shit, you give me a 1,000-core processor, I give you a 1,000-core processor, and I expect you to get a 1,000-fold speed up. How much of all the things that your program is doing, how much of that has to be sped up, percentage-wise? In other words, you have to figure out what portion of the program has to be able to figure out how to use all 1,000 cores in order to get a 1,000 speed up. And the answer is 99.9%. If you just stick 1,000 in here and do some arithmetic, you discover that F is 999 over 1,000. And you go, wait a minute. I mean, basically to use 1,000 cores, I basically have to be almost perfect in causing everything to speed up. So that's a real challenge. Most of our programs we want to run don't have that amount of parallelism available to them. There's a motorcycle on our roof. Okay, so alrighty. So the answer sort of is that multi-cores are good, but you have to, the amount of speed up you can get often has very little to do with the number of cores somebody has just sold you. Okay, so let's look at some of these other level types of parallelism, and keep in mind Amdahl's law as we sort of go here. Okay, so what we have is things that involve doing similar operations on many, many, many pieces of data. There's some common examples. You own some in your machine. Can anyone think of a couple of computations that we might perform quite frequently that involve a sequence of the same operations but are just on different data? What sort of things do you do every day where that would be a wonderful engine to have? I'm sorry? Image convolution, so more generically, lots of image processing, particularly image decompression, which involves all sorts of operations on the image in parallel, is a great example. Any sort of MPEG, MP3, all of those represent vast opportunities where we're really running the same computation, but just on different chunks of data, right? So it turns out that almost all machines contain both some amount of graphics processing and then rendering images onto screens. So, these GPUs are basically these huge, 512 cores all running in parallel on different scene elements, and then the stuff gets merged together. So the idea is that these are, that we actually have a lot of different data, but we want to do very similar computations. What architecture would we design to do that? And so we get what we call a SIMD architecture, S-I-M-D. So this stands for multiple data. And as you might have guessed right at the moment, this stands for single instruction. So what we do is we build architectures that basically have many functional units that are identical. We have one instruction and we yell, add. Anybody ever watch those, or I guess they call them sword and sandal epics? There's always the scene where you see the big, sweaty, heavy guy in the back beating on the drum in the galley, right? And everybody's roaring like mad. And the idea is that there's one instruction, stroke, 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 and then you have lots of people doing it, and you get a lot of effective horsepower out of that. Well, it works for computation too. So here's the big sweaty guy who's off here deciding what operation to be performed, and it's all being performed on tens or hundreds or thousands of pieces of data at the same time. Okay, so that's sort of the notion of SIMD. Every modern processor contains some sort of what they call multimedia instruction set. There's had different names over the years. SSE, ASE, MSE. These are all different sort of instructions that are designed to basically operate on many bytes in parallel. So you can do byte level arithmetic on 8 or 10 or 8 or 16 or 128 bytes in parallel. And that's what is used to make your Intel processor actually decode MP3s pretty quickly. Okay. Another common scheme is to basically imagine a vector architecture. So instead of writing your program consisting of a lot of loops and things like that basically go step through the array and do things, what we do is we basically treat the data type not as single integers, but as a big vector. Okay, and Seymour Cray built machines. The Cray machines were, the sort of canonical vector machine. So you basically say, load up a vector into a vector register. So think of a vector register as holding, 100 or 1,000 elements. And so this load instruction is streaming a vast amount of data. In some ways we're sort of explicitly managing these huge cache lines where we're bringing them in and putting them into things, vector registers, which you can just think of as a giant cache line that we're managing explicitly. And then we can perform operations where we say, take everything in this vector and everything in that vector, add it together element by element, and store it in the third vector. So vector machines are really, they're quite attractive for certain types of processing. They work really, really well. So vectorizing the code was, when I was young, everybody was running around saying, how can I build a vectorizing compiler? And it works best if you basically give people a programming language where the vector is a natural data type. Right, because then they haven't broken down a sequence of operations like that. And it's a little hard to look at that code and say, oh, that turns out to be a vector operation. Right? So it's a little easier to see it when it's written this way. Okay. So vector machines have had their heyday. There's still some proponents of vector machines as the right way to get high performance computing, and certainly for certain types of fancy Dan simulation code, numerical simulation code for engineering and science, vector machines still do pretty well. Okay, so here's there's lots of different sort of vector processing implementation. Maybe the most famous one these days are the GPUs. We have simple GPUs in our machines. Maybe at home you have a giant desktop with this honking card in it that's all you can see is fan, right? It's covered in this huge cowling and these high-speed fans that are trying to keep it cool while it busily melts itself off the board, performing all these vast numbers of floating point operations each second, right? And the way it's able to get a vast number is not that it can do any one floating point computation faster than your Intel processor. In fact, it can't, but is doing 512 of them in series, in parallel. So that's how it can get so fast. Alrighty, so that was, data parallelism. Data parallelism sort of makes sense. Typically, you handwrite the code to do data parallelism. The most effective. Anybody ever tried doing any Bitcoin mining? Yeah, there was a time at which everybody sort of said to themselves, maybe if I could mine Bitcoins, I'll become rich and don't have to do my PSET tonight. And so the idea, so there's an example of something where using the parallel processing your machine, using those fancy SIMD instructions, using GPUs, those are all places where people put an enormous amount of effort handwriting programs to take advantage of those instruction sets and the data architectures they have in them to do very specific computations. Those are the most successful use of that machine, of those sorts of machines. A different sort of parallelism is this notion of we just basically have independent threads. So we're going to go from SIMD, we're going to basically turn this to multiple instructions, multiple data. We're going to go to MIMD. Okay, and pretty much everybody's processor these days is a MIMD machine. You have maybe 2 cores or 4 cores or something like that, multiple threads. Okay. And it has a fairly simple idea. What we're going to do is each thread is running independently. If they need to communicate, they do it through shared memory. That's the medium in which they communicate. More modern processors, which are about ready to be announced, will, instead of having a shared memory, will have a shared communication network. And it will be your job to send messages to processors if you want to share information with them. So it's very, this is a simple model, but it causes the memory to be pretty much of a bottleneck as everybody tries to share things in one main memory. The message passing parallelism turns out to be, the new Intel, Knights Landing processors with, I forget how many it is, 64 processors or 76 or something. They start using message passing rather than a big shared memory. Okay, but we'll talk about a shared memory machine or message passing, where everybody basically, sends things across a network. So that's how, thread level parallelism is going to work. And you say, okay, this is all really good. The interesting part is, how do we do this shared bit? Message passing is pretty straightforward. How do we do this shared bit? So let's think. You say to yourself, maybe this will actually work. Let's think this through. So what we're going to have is 4 beta cores here, and each of them has their own cache. And the reason that we have a big cache here, a level 1 and a level 2 cache typically, is that what we want to do is to say, look, most of the memory operations, 90+% of the memory operations are going to be soaked up by the cache. The cache will have a high hit rate, and so this is asking for certainly an instruction every cycle, and maybe a write, a load, or a store to a piece of data every 4th, 5th, 17th cycle, whatever it is. If that can be handled in the cache, the amount of traffic in the shared part of the system might be low enough that the shared part does not become a bottleneck. But we have to be a little careful, and here's an example. So we're going to start off where we have 2 processes that are running, one in core 0, one in core 1. And everybody has decided that currently x is equal to 1 and y equals to 2. That's the value. That's what the value you would find in main memory, and that's the value you find for each of those memory locations in the cache. Now let's see what happens when process A and process B continue running. And A sets x equal to 3 and prints y, and B sets y equal to 4 and prints x. Okay, so how does this work? Let's just sort of follow along what happens here. So what are the possible outcomes? Well, these 4 instructions might be executed in any interleaved order. The process A will be modifying the x variable, and process Y will be modifying the process B will be modifying the y variable, and we can say, okay, so there's the modifications that are happening after the first statement, and then a bunch of prints happen. And what's really neat about this is that you look at this and you go, okay, this is pretty good. Depending, no matter how I interleave it, at the end of the day, A prints 2 and B prints 1, because those were the values of the y in this cache and the x in that cache. Okay, and you sort of say, well, that's great, let's build it. Let's go off and actually, this seems like it's sort of working, but you should be getting a little nervous at the moment, because what we discover is that people are no longer really agreeing on what the values of x and y are. Right? Even though the values of x and y have changed in some global sense, after the execution of these programs. Okay, it turns out because of the caches and the updates that happen to the caches, that information isn't being made widely available. In fact, we designed the system to sort of limit the amount of communication. Okay, now let's talk about what we would like to have happen. And so we're going to introduce this notion of semantics, okay, of what it means for multiple programs to be operating concurrently in parallel, to say, look, it should correspond to the interleaved execution on some single machine, some time-shared machine, where the reads and writes both go to the same cache, okay? And if we actually look at that, we look at the execution here, what we discover is, depending on the exact order of interleaving, we can get A and B to print different values. What's absolutely fascinating is that the printing 2 and 1 is not one of the things on that list. Okay, so now you should sort of say to yourself, what is it we mean about correct operation of a program? We have 2 threads, 2 processes running, and they're both making changes to variables. What would be our standard for correctness? And it turns out what you choose will affect a lot the hardware we have to build and the performance we're able to achieve. Yes? Right, so this is basically arguing that you serialize it. There's many different ways to serialize it, and you pick one of those serializations. Okay, this is so-called sequential consistency. That's the name for this particular semantics, right? Where the outcome, is only a legal outcome if it corresponds to some sequential execution of the program. And so that's a so-called sequential consistency, is so-called a strong consistency criteria. And so the possible values of 2 and 3 and 4 and 3 and 4 and 1, okay, correspond to at least some interleaved execution. This answer is just wrong by any standard that we just established. This answer is inconsistent with sequential consistency. Right, and so this is a little bit awkward. Right? Or we've designed here we have, this thing, but, caches are supposed to be invisible, but now they're changing what our programs are printing. Okay, so this whole notion of going to multiple cores and naively using caches has gotten us into deep guacamole. And what we're going to have to do is to fix it. Okay, and once again, we're going to have to invent some hardware mechanism that will notice when information has to be interchanged between the processors. Okay, so what we're going to do is, look, when we're sharing a value, if you change it, you have to let me know, and vice versa, of course. So the idea is that if we're not sharing, we can go off and just use our caches however we want. If we are sharing a particular memory location, if we happen to both have that in our cache, now the caches have to tell each other when one of us changes that information. And so there's a fairly interesting, to me fascinating scheme in which the caches are not only simply re-interacting between main memory, they're using the same bus to pass messages to each other about, I know that you're sharing this, and so I'm going to tell you that I'm just about ready to change its value. So your copy is no longer valid. Okay. The goal in designing the protocol that we're going to use, when do we communicate and what do we actually say to each other between the caches, we want to pick such a thing that we're going to minimize the amount of communication, because if we do too much communication here, this shared bus will now become a bottleneck and limit the performance of the entire system. We might as well not have the caches. Okay, and so what we're going to do is to have a more sophisticated way of labeling cache lines. We used to have it being valid or invalid or dirty. Well, we're going to have a more sophisticated state, right? Okay. Here's how it might work. So this is the so-called MESI protocol, M-E-S-I. That corresponds to each of 4 states. Invalid is pretty simple. I don't have that line in my cache. So this is for every cache line everywhere in the system has this state tag, okay? And it has 1 of 4 states. Invalid, there's nothing on this cache line. It's like if it's not there. Don't worry about it. When I go off and I read a memory location, I have a cache miss, and I read it into my cache, one of 2 things will happen. Either I'll read it, and all the other caches which are they're snooping on my memory reads, they're looking on the shared bus and going, oh wait, Chris is reading that location. If they also have a copy of that location, they will set a separate flag on the bus saying, psst, it's shared. I have a copy too. So when I do a read, I get the information from memory, okay, but I also get the indication of whether anybody is sharing it or not. If nobody is sharing it, I mark that cache line as exclusive. I have a copy of it, and I know no one else has a copy of it. That means I can change it with impunity. Okay. If it is shared, I will know that too. So as I bring in the cache line, it's either marked exclusive or shared, depending on what the Snoopy bus tells me. If it is shared, now we can both read it, but as soon as one of us writes it, okay, we're going to have to communicate. So we're using the state bits here to basically indicate when we have to communicate. So exclusive locations are ours alone, and we can do anything we want to them. Shared locations say there's communication that will be necessary. The cache will take care of it, but now the cache knows there's other caches out there with this same memory information, and now whenever something's going to happen to it, we have to update things. Now notice if I had it exclusive and you read it and I marked it as shared, it'll be marked shared in your cache. Of course, then I would have to change it to be marked shared in my cache too. And I know that I need to do that because I watched you read it and I told you it was shared, and now both of us will say it's shared. Alrighty. And the final state is that I've had an exclusive use location that I wrote into, and now it's modified. And so now when somebody else reads that location, first of all I have to tell the memory system, psst, don't answer because you don't have the right answer. Okay, and now it's up to the cache that holds the modified, only one cache will be in the modified state. Okay, and everybody else will be invalid, so when they access it, they'll say, oh, I got to read it, and now the cache that holds the modified state has to say, oh, I'll supply the answer. And maybe I'll write it into main memory at the same time. As long as I'm putting the data on the bus, the memory system might as well write it too. Okay, so here's MESI, modified, exclusive, shared, invalid. These states are all about keeping track of when things are shared and when who has to communicate what to whom. Okay, so the cache actually has two customers. It has transactions that are coming from the CPU, and it has transactions that are coming on the bus. And the cache is busy updating the state depending on what the CPU is asking it and what's happening on the bus. Right, so the cache has now become much more complicated, at least the state update stuff. There's some interesting things about taking operations that take a long time. For example, if you try to write something that isn't in the cache, you get a cache miss. Well, in a modern processor, those go into a write buffer or a store queue. And the CPU gets to go on. Meanwhile, the cache is off fetching things from memory, perhaps marking them shared or whatever. And finally, when the cache line finally is refilled in the cache, it actually completes the write into the cache. So it doesn't make the CPU wait on a write miss. It says, go ahead, you keep going, I'll keep track of writes that I need to do. And the same thing with invalidates from the bus. It might take a few cycles before the invalidate actually happens. And then we have special instructions that tell us, okay, I want to make sure everything that I've asked to have happened has happened, so I'm going to stop here and let's start me running again when the queues are empty. So the so-called memory barrier instructions. This is an unreadable diagram, but the key is to go look here. This is actually a detailed thing that tells you exactly how a MESI cache works. How the state transitions all work, when do they happen, under what circumstances, under what communication messages from both the CPU and the cache. The thing that's interesting that Intel actually implements a MESI cache that has 5 states. It has a 5th state, which indicates a special situation about who's actually going to supply the value if the memory system doesn't have it. Okay, deep breath. And you say, whoa, another whole pile of transistors just got added to my system to deal with this small thing that our system was going to compute the wrong answer if we did it naively, just like we had to do bypassing in pipeline processors. Okay, and you are the proud owners of a MESI, Snoopy cache system in order to make it so that you can write programs without worrying about whether you're sharing a location or not. The system will do the right thing. It's interesting to think about, are there different models of consistency? So that, for example, the notion of a weak consistency. So we talk about strong consistency. It corresponds to some interleaved execution. Weak consistency is just that an individual processor sees reads and writes that it does happen in the right order. In other words, it will never be, so if it wrote a location and then it read it, it would say, of course, I would expect to see the updated value. However, the weak consistency doesn't involve anything having to do with sharing. That's sort of outside the model. So a weak, if your system, if you chose a weak consistency model, our naive cache implementation would in fact work correctly. I mean, that would be a correct execution. So there's a lot of work these days on exactly what memory consistency model we should be using in order to build very high performance processors that involve sharing. Okay. And then special instructions that let us, sort of all get on the same page if we have to. Okay, so we've done pipelining and superscalar and data level parallelism. We've really worked hard on those for many, many years. There's a little bit of improvement to be made there. I'm not sure there's a whole lot. I mean, there's the technological improvements we can make, but architecturally we sort of mined those out. We really have a limit on single threads, but we have a wonderful processor as an example. We have a processor up here, okay, that's massively parallelism, has really shitty communications. I mean, the bandwidth, between the neurons is very small compared to what we're used to. It turns out, of course, it's very parallel, so the collective bandwidth is pretty large. But what we're trying to, you might say, well, are there places we can look to get inspirations for what new architecture should be? And the answer is, we need sort of new thinking about all of this. And guess what? It's going to be your job. Right? You might say to yourself, well, if everything is done, why am I bothering to study architecture? There are some huge problems remaining, happily, and they're going to be your problems to solve. So, alrighty, with that, we'll stop there. Have a productive weekend, and we'll see you next Tuesday.